Have you ever wondered why does hemoglobin look red? Because you know every breath we take depends on hemoglobin, right? In hemoglobin, a deep red coordination compound of iron is present, and this iron carries oxygen in our blood. But the question is, why does hemoglobin look red? Again, you must have seen some plants, maybe some green plants. But why plants are green? The answer lies in chlorophyll. You know chlorophyll, right? In chlorophyll, a coordination compound is present with a magnesium ion at its center, and this brilliant green pigment absorbs red and blue light but reflects green, giving their leaves a characteristic color of green. And lastly, why a copper ion when reacts with ammonia, its color changes to deep blue. Interesting, right? Well, in these three things, we have seen a coordination compound is present, right? So to answer these questions, we need to peek inside the bonding of coordination compounds. So the bonding in coordination compounds started with Alfred Werner. Werner had already explained the coordination number and structures of the complexes, but his theory could not explain how metals bond with ligands at the orbital level, or why these complexes show such interesting properties. That's where another scientist named Linus Pauling came, and he gave Valence Bond Theory. And this Valence Bond Theory helps us to understand how the central metal atom uses its orbital to bond with ligands, and how the geometry of complexes like tetrahedral, square planar, or octahedral arises. So in this video, let's explore how orbitals rearrange themselves to form these fascinating compounds and see why VBT or Valence Bond Theory was such a big step in coordination chemistry. So here is the first point. In a coordination compound, the metal atom makes its orbital empty to acquire the lone pair electrons coming from the ligand. So here two things we have to pay attention. What? The metal atom makes its orbital empty and the ligand must have a lone pair electron to donate. So through this, it explains the bonding between a central metal atom or ion and surrounding ligands in terms of orbital overlap and hybridization, from which we can find out the geometry of these coordination compounds. So first of all, we have to understand how the valence bond theory in coordination compounds is different from the covalent compounds. For this, first we will look at the covalent compounds or the covalent molecules. What happens here? In covalent molecules, as you know, two atoms share their 1-1 unpaired electrons and their orbital overlap to form a molecule. Like two different atoms are there. Here is the atomic orbital of one atom and here the atomic orbital of another atom. They both have 1-1 unpaired electron with opposite spin, and these atomic orbitals overlap. When the atomic orbitals overlap, they form a molecular orbital in which two electrons are present, and this is known as molecular orbital. Here both the atoms shared their one electron. But in coordination compounds, what happens? A metal orbital is present, a ligand orbital is present. So here the metal orbital have a empty orbital and the ligand orbital have paired electrons or two lone pair electrons. Here they both do not share their electrons. What happens here? The ligand donate its lone pair electron to the metal orbital and makes a coordinate bond. And when the orbital overlapping takes place, a coordination compound forms. So this is the basic difference between a covalent molecule or covalent compounds and coordination compounds. So one thing is here. What happens? The metal orbital was empty and it accepted a lone pair electron from the ligand orbital. So when the metal orbital accepted one lone pair electron, we can say the metal is a Lewis acid, and the ligand orbital, it donates the lone pair electron, so it is a Lewis base. So let's discuss the geometry in coordination compounds. There are different kind of geometry. One is octahedral geometry. For octahedral geometry or for octahedral complexes, the metal vacates its 6 orbital to accept the lone pairs coming from the ligand. Okay, so this is the n-1d orbital, this is the ns orbital, and this is the np orbital. So this is the orbitals of the last cell and this is the penultimate cell's orbital. So when these orbitals are involved in the electron transfer and accepts the lone pair electrons, then the hybridization is d2sp3. Okay, so it involves the n-1d orbital or the inner cell orbital. Here is another case in which ns orbital is involved, np and nd orbitals are involved. But in octahedral complexes, 6 vacant orbital should be present. So for this, 1, 2, 3, 4, 5, 6. So let's take this. So 6 orbital makes, what happens? 1s, 3p and 2d. Its hybridization is sp3d2. So but it involves the d orbital of outer orbital complex of the outermost shell. So this is known as inner d orbital complex. This is known as outer d orbital complex. So this is for octahedral complexes. Okay. So what will happen to the tetrahedral geometry? So for tetrahedral geometry, the hybridization will be sp3 or sd3. Okay. So first discuss about sp3. So again we have to take n-1 d orbital, ns orbital, np orbital. If the orbitals participating in coordination bonding is s and 3p, then it is known as sp3 hybridized. Again, sd3 also can be formed in some special cases, like in MnO4-, there is a different concept. ns, n-1d comes after the ns and np is present, and here these 4 orbitals are involved in the coordination bonding, ns and n-1d, and the hybridization will be sd3. So this is a special case, we will not talk about here. So let's talk about the square planar complexes. For square planar complexes, it will also involves n-1d, ns, np orbitals, and for square planar complexes, 4 orbitals are involved. If the 4 orbitals are involved, like 1 from the n-1d, 1 from ns and 2 from p, it is known as dsp2. Okay. For here, another special case is also present. That is known as 3 orbitals involved, 1 from ns, 2 from np and 1 from nd. And in this case, the hybridization will be sp2d for square planar complexes. But it is also not in our syllabus, so we will not talk about it. So let's talk about some key points. One is magnetic moment. Always remember, magnetic moment plays a very strong role in the hybridization or shape of a molecule. And it is of 2 types. One is paramagnetic, one is diamagnetic. In paramagnetic compounds, unpaired electron is greater than or equal to 1. That means in the orbitals of the central metal atom, unpaired electrons are present. But when in the metal ion or metal atom, unpaired electrons are absent or equal to 0, then the compound is known as diamagnetic. So one point we can discuss here, that more is the number of unpaired electron, more will be the magnetic moment. So to calculate magnetic moment, we have a formula called mu is equal to n into n plus 2 root over, where n is equal to number of unpaired electrons. So let's discuss about ligands. So ligands can be of 2 types. One is strong field ligand and one is weak field ligand. So from this magnetic moment data, we can conclude which one will be the strong field ligand and which one will be the weak field ligand. So let's talk about this. So if mu value is not equal to 0, that means unpaired electrons are present. Then if unpaired electrons are present, then it is paramagnetic in nature. If they are paramagnetic, then the ligand is weak field ligand. But it is a complete assumption. There are some exceptional cases in which unpaired electrons are present, but the ligands behaves as strong field. So we can say the valence bond theory or VBT is completely experimental. There is no concrete data. It cannot distinguish between a weak field ligand or strong field ligand. Okay. So for weak field ligand, mu value is equal to 0. So if mu value is equal to 0, unpaired electrons are absent, compound is diamagnetic, and the ligand is strong field ligand. Okay. So the strong field ligands causes electron pairing. Okay. So here is a simple trick we can use to remember which ones are the strong field ligand and which one are the weak field ligand. If the donor atoms are sulfur, halogen and oxygen, then the ligands are known as weak ligands. If the donor atoms are nitrogen, carbon and phosphorus, then the ligands are known as strong ligands. Okay. So let's understand the valence bond theory, or how does the ligands and metal bonding takes place, through some examples. Okay. So first example I have taken here is COCN63-. For this, a condition is given. The condition is mu value is equal to 0. If the mu value is equal to 0, as we have discussed, the ligand is strong field ligand. And for strong field ligand, pairing occurs. So for this, I have to first calculate the oxidation number of cobalt. For this, oxidation number can be calculated like this: X plus 6 into minus 1. That means 6 ligands are present, and Cn or cyanide is a negatively charged ligand. So minus 1 is here, is equal to overall charge is minus 3. So when you calculate this, X comes plus 3. So the oxidation number of cobalt is plus 3. So let's first draw the electronic configuration of cobalt. It is argon 3d7 4s2, and let's draw its atomic orbital. Again we will draw the electronic configuration of cobalt 3 plus ion, that is argon 3d6 4s0, because for the 3 plus charge 3 electrons are donated from 4s2 electrons, from 3d 1 electron. So for 3d6 4s0 we can draw the atomic orbitals like this, and here we can see 6 ligands are present, so we can write it here. They have lone pair of electrons. So what will happen? Here mu value is equal to 0. That means it is a strong field ligand. So for this, the unpaired electrons will get paired first. So how does will it pair? So this electron will pair with this electron will pair, and they will stay in opposite spin in one orbital. So for this, 6 vacant orbitals are present. So what will happen? The ligands will donate their lone pair of electrons to these vacant orbitals and make a coordination bond. So let's write these electrons like this with opposite spins. Okay. So here, how many bonds formed? 1, 2, 3, 4, 5, 6. And let's put this into a bracket. 2 from 3d orbital, 1 from 4s orbital, and 3 from 4p orbital. So its hybridization will be d2sp3. So let's write this. Hybridization is d2sp3. Geometry will be octahedral. We can write it inner orbital complex or low spin complex, or it is also called a spin paired complex. So let's talk another example with some different conditions. Okay. For this, I have taken an example of CoF₆ 3-. Here the condition is mu value not equal to 0. For mu value not equal to 0, the ligand is weak field ligand and it does not do pairing. For this, first we have to calculate the oxidation number of cobalt, X equal to +3. For this, let's draw the electronic configuration of CO. It will look like this. And again, for CO3 plus, the electronic configuration will look like this, just like this. Okay. So here, what do we see? We see the ligand is F and mu value not equal to 0. That means it is a weak field ligand, so it cannot do pairing. So if these electrons does not get paired, then how do we find 6 vacant orbitals? So for this, another orbital of 4d comes here, and we have 6 fluorine atoms or fluorine ligands. So let's put these fluorine ligands here. They have lone pair electrons. So what will happen? These fluorine ligands will donate their electrons to the vacant orbitals of these orbitals of cobalt, and the electrons will present like this with opposite spin. So let's put this into a box. So the orbitals involved are 1s, 3p and 2d. So for this, we can write the hybridization as sp3d2. Okay. So now we can discuss some points from this example. Like the hybridization is sp3d2. Geometry will be octahedral. The d orbital involved is the outer d orbital. We can see here. So it is outer orbital complex or high spin complex or spin free complex. So here 4 unpaired electrons are present. So we can calculate the magnetic moment value. The magnetic moment value will be 4.9 Bohr magneton. So let's discuss one last example, that is MnCN6 3-. Okay. And for this, the condition is given that the molecule is paramagnetic with 2 unpaired electrons. Okay. So for this, the orbital diagram will look like this. 4 electrons in the 3d orbital and 0 electron in 4s orbital. Okay. So here cyanide is present, and cyanide is a strong field ligand. It do pairing. So for this 6, but here the condition is molecule is paramagnetic and 2 unpaired electrons are present. For 2 unpaired electrons to be present, 1 electron will do pairing with the another electron of this orbital. So it will do pairing like this and stay as the opposite spin. Here you see cyanide did pairing of 1 electron, and the hybridization will be d2sp3. But why it did pair 1 electron only? Why other 2 electrons did not get pair? So this is something valence bond theory could not explain, and we can say this is the limitation of valence bond theory. And always remember that the valence bond theory is completely experimental. It only deals with the bonding, how the ligands donate their lone pair electrons to the vacant orbital of central metal atom or ion, and how the coordination bonding takes place. It tells us about the geometry. It tells us about the inner outer orbital complex, but it did not explain on what basis we consider a ligand as strong field or weak field. And it did not explain why strong field ligand causes pairing and weak field ligand does not do pairing. And again, it does not explain the color exhibited by the coordination compounds. Only it deals with the bonding. Okay. And another limitation is, as we know, in octahedral complexes, all bond lengths are same. But in COH2O6 2+, it does not have the same bond length being an octahedral molecule. It will look like this. What happens here? Here the axial bond length is more than the equatorial bond length. It did not explain about it at all. And also, VVT made a lot of assumptions. That's it.